Hello, everyone. I'm Lucia. Well, first of all, thank you so much for joining us today. Let me start by introducing ourselves so that we can go with the session. So I'm Lucia. I'm part of the data science team here at CARTO, and I'm currently working at the intersection of product development and also client solutions. And I've recently been focusing on areas like territory planning and also applying foundation models to spatial data. So that's why I'm joining Caitlin today to discuss about how CARTO integrates these embeddings into the platform and how can users leverage all the power that they have. Caitlin, if you want to introduce yourself as well.
Yeah, hi everyone. My name is Caitlin Tario, and I'm an Earth Engine solution scientist here at Google, based in New York City, where I work on mitigating carbon impact from deforestation and making geospatial data more accessible and useful. So thank you for having me. Really excited to talk about our data set today.
Okay, so let me start by presenting the agenda. The first thing that we are going to be discussing is how to use AlphaEarth for spatial analytics. Kaylin will cover this part. She will explain what are the embeddings, how have they built the satellite embeddings, and everything related to the product itself. And then I'll jump in to discuss how are we integrating these satellite embeddings into CARTO so that you can use them for your spatial analysis. And then I'll guide you through some live demos so that you can see in action how these embeddings work. And lastly, we will run some Q&A so that you can answer any questions that you may have. So, Caitlin, the floor is yours now.
All right, thanks so much. Next slide, please. So jumping right in, everyone online today understands the enormous value that geospatial data brings to environmental data science, providing sort of key information on the when and where to fuel analysis of like what, why, and how. Next slide. Sorry, it incrementally advances. But the problem is I'm sure many of you know, right? Working with satellite imagery is hard. So traditional analysis requires a substantial amount of pre-processing, whether it's dealing with atmospheric correction and clouds and optical imagery, speckle filtering, noise with radar data, harmonizing different data sources. And so effectively leveraging that satellite data requires a lot of machine learning expertise for things like feature extraction, finding the right algorithms, building custom models. And doing that is really time consuming and expensive and slow. Next slide, please. And so, those things have always been major barriers to using satellite data in general. And so we believe that geospatial AI is really the answer to this issue. So making data streams more accessible to generate faster insights and decision making. And so, next slide, please. Our solution to this sort of geospatial data overload is the AlphaEarth's foundational model and the satellite embeddings data set. And so AlphaEarth's foundation is a geospatial AI model developed by Google DeepMind in partnership with Google Earth Engine. And so it integrates petabytes of Earth observation data across diverse geospatial data types. So optical and thermal imagery, radar, LiDAR, and climate data, to create sort of a unified digital representation of the planet. And this representation is called an embedding. And so embeddings are learned compact feature vectors that sort of summarize complex, high-dimensional spatial, temporal, and multi-source data into a sort of low-dimensional space where the distance or similarity is meaningful. And so this model has been run at scale across the globe to produce the Google Satellite Embeddings dataset, which is a global data set of pre-computed, information-rich features that are analysis-ready. So you can think of it as sort of a virtual satellite. So these embeddings have been packaged and summarized into 64 dimensional representations or bands, similarly, at a 10-meter spatial resolution for every year back to 2017. Next slide, please. So really quickly, what is an embedding? Because again, this is very, a hot topic in the geospatial world. Google's not the only one that's doing this. But, an embedding is really like a special feature layer that packs a year's worth, in our case, of complex multi-source data into each pixel. So you can think of it as sort of a learned super index that replaces traditional raw imagery and complex hand-engineered features. So say you were doing a task like mapping urban expansion, instead of finding which sensors are most relevant to your application and manually deriving features that are useful for this task, like finding temperature and albedo features, you can simply use the embedding data set. So sort of substituting this for traditional imagery. Next slide, please. And so the model's power really comes from its multimodal approach. So we assimilated data from over a dozen sources like Sentinel-1 and Sentinel-2 optical imagery, radar data from Sentinel-1, I meant previously a Sentinel-2 and Landsat for the optical Sentinel-1 radar, JEDI LiDAR, climate and topographic data as well. And so this foundation allows the model to learn sort of a single unified feature from sparse, non-uniform data that would have been impossible to analyze all at once using traditional methods. Next slide, please. So I just want to say a little bit about sort of the temporal context, because this leads to the question of how all of this complex time series information is sort of synthesized across different sensors and captured in a single static vector. And so traditional analysis sort of relies on sparse, non-uniformly sampled records. So in that top panel there, those sort of scattered satellite observations. And the AlphaEarth Foundations model sort of resolves these scattered observations by treating all of them as sort of like a video and allowing it to synthesize a continuous record for a location. And so I do want to say that the Google DeepMind team has put an enormous amount of effort into harmonizing and standardizing these data sources. There isn't enough time for today for me to fully explain this, so please, I encourage everyone to see the archive preprint that I have linked on the slide below there, which I'm sure will share resources with everyone afterwards. But suffice to say, this means that the resulting embedding successfully encodes the full annual temporal trajectory, so capturing things like agricultural phenology or seasonal water dynamics, and also changes over time. So even if the actual satellite data sources were sparse or obscured by clouds, right, we're leveraging all of them at once, and so we're sort of overcoming that issue. Next slide, please. And so this model incorporates both temporal and spatial context. So on the left, you can see that the final embedding for this little red target pixel in the center of the image is generated using data from a 1.28 kilometer squared spatial window. And so, which we have in this little box around it, right? So the embedding is also learning the spatial context, not just whatever is immediately over this pixel itself. And then we're also learning, the full calendar year of multi-sensor image acquisitions that are shown on the right. So with this model, you're getting both the temporal and the spatial context, which is really useful. Next slide, please. So what can you do with satellite embeddings? As I said before, the result of these embeddings are really a pre-processed feature layer that's ready to be used as in substitution for images for machine learning applications. And so for data scientists, you can perform sort of all the standard analyses you would normally do, like classification, regression, and change detection, but with the added benefit of achieving sort of higher accuracy with significantly less training data than traditional methods, right? Because the low noise embedding space that the model has created means that you should need sort of fewer training data points to achieve the same or better, higher quality results. So just as a quick anecdotal example, some of my work here at Google involves mapping tropical commodities like cocoa and coffee for supply chain sustainability initiatives. And previously, we needed to use millions and millions of training data points, which is really costly to collect and curate. And now with embeddings, we can achieve actually a better classification result with fewer data points because we have that suite of rich information from the optical and LiDAR and radar data all synthesized. So that's really been great. And embeddings also unlock sort of new applications like similarity searches, right? Where we can sort of scan the globe and instantly find all locations in the world with a similar surface and environmental condition to the embedding space. And so next slide, please. I went really fast. So, to wrap up, just some high level takeaways. The satellite embeddings really deliver sort of three core value propositions for your work. One being just faster insights, right? So we can eliminate heavy pre-processing and complex feature engineering to replace with just a single analysis-ready layer, which is awesome, in my opinion. Secondly, this enables really just new analyses, right? So we can perform tasks like global similarity searches or unsupervised clustering on these embeddings to reveal sort of hidden patterns that you wouldn't really find even using traditional multi-sensor approaches. It's just sort of night and day with the change and added rich information of these embeddings. And most importantly, and lastly, just better predictions, right? So the model's low noise, information-rich embedding layer is yielding better accuracy and requiring just a fraction of the labels needed for traditional methods. And so with that, I will turn it over to Lucy for applications.
Thank you so much, Caitlin. That was a really insightful deep dive into satellite embeddings. So now let's switch with topics and discuss about how CARTO does actually integrate the satellite embeddings into their platform, and also what is CARTO's role in this geo AI landscape that it's currently going on. So first of all, our main goal here is basically that we want to act as a bridge between geospatial foundation model research and real-world analytics, which we've actually been working closely with Google Research to bring foundation models into real-world spatial analytics. This means that what we want to do is connect these models directly with the data and the tools that analysts and data scientists use already on their daily basis, so that they can use this data or these models very easily. In order to that, we also want that all this research that's been done by Google and other companies translates actually into an impact. Because we want that users that use these embeddings and these models actually get best predictions and can make better decisions that actually create some business value to them. So this is very important here as well. Of course, we want to make geospatial AI available to everyone, not just machine learning experts. This means that we want analysts, data scientists, and developers to use these models without the need of training them or fine-tuning them, because as Caitlin was explaining before, this takes a lot of effort, takes a lot of time, and a lot of computational resources. So if we provide these models directly to the end users, it's much more easier for them and faster for them to work with them and get insights from their data as well. And of course, this is part of our broader effort to grow the community of practitioners using geospatial foundation models, because what we want to do is to promote the use of these models so that everyone can leverage the power that they have. Now, I want to discuss how do we actually integrate these geospatial models into CARTO. We actually do this making use of CARTO workflows. For those of you who are not familiar with workflows, workflows is a part of the platform that allows users to visually create their analysis on a step-by-step process, trying to write the less amount of code as possible. So this is very visual and this is very user-friendly, because users just need to drag and drop components to the canvas, connect these components, and then easily run their analysis without the need of being actual experts in SQL, for example. This is very good because this allows for seamless integration of these models into CARTO, because we can just have them, these embeddings available as components, so the users can drag and drop the components into the canvas and enrich their spatial pipelines. So as I was saying before, no need to have any machine learning expertise required, because we are already providing the models for you to use. And this is very interesting because you can combine the models with your own data to get insights, analyze relationships, and extract trends from your data, combined with the embeddings, for example, improving the performance of your models or things like that. And since all of this is running under CARTO's scalable infrastructure, this makes it very easy to run analysis on large data sets, automate the analysis, share the workflows with stakeholders or other users within the organization. So this way, this is very, very straightforward to use. For now, we have this extension package that it's called Geospatial Foundation Models available, that has three embeddings available for users to use, including the satellite embeddings that we've been discussing for now, and 2 other models from Google, which are the population dynamics foundation models, which are also available right now. Why this matters for you, why this is important for the end users? Because we want you to be able to do more with less effort. That is, with using these embeddings, you can get faster insights without building the models from scratch, as we were saying before, which is very, very useful because it reduces the effort, but helps us get better results and more precise results when we are working with this type of embeddings. Apart from that, this is very useful because it allows us to expand our toolkit, because we uncover new types of analysis that we may not be working with them before, because we did not have these embeddings available for us. For example, this similarity search that Caitlin was explaining before, or for example, fine-grained predictions with models that are enriched with these embeddings apart from traditional spatial features. And talking about traditional spatial features, using embeddings also improves the decision-making process, because including these embeddings in our analysis and in our models allows us to include also like richer signals that complement these traditional features, because these embeddings contain information hidden that traditional features may be missing. So if we combine these two, we end up with more informed decisions that are very useful when working with different use cases. And the good thing about this integration is that right now this is a very huge topic. There's a lot of research being done on these models, so these models are evolving all the time. And the good thing about having the embeddings integrated directly into workflows is that when these models evolve, we can just make them available through the same platform, that is through workflows. So users do not need to do any type of complex engineering to update the models. They just need to drag and drop the component with the updated version of the models and then directly update their analysis. So these are future-proof and very, very easy to update and very easy to integrate. Now let's talk about the satellite embedding component. As I was saying before, this is part of an extension package that you need to install into workflows. The installation is very easy. You can take a look at that in our documentation, or ask any questions if you're interested. But then once you have it installed, you just need to drag and drop the component. And how it works is you need to specify an input and a set of settings, and then the component will retrieve the summarized values for each of the 64 embedding dimensions that this model has. So as an input, we need to connect this component to a source table that contains the geometries or the geographies for which we want to extract the embeddings. Then we need to also specify the time range for which we want the embeddings, for example, in this case, from 2020 to 2024. And then the component will summarize the values for this time period and for these geometries that we've specified. And we will get the results directly. You will see this later in the demo, how the results look like, so that we can then connect these to other components to run analysis, run predictions, and get insights from the components. One important thing to mention here is that we are summarizing the values for each of the input geometries. So that's why we are allowing the user to specify the function that they want to use to reduce the original embeddings. Usually the mean or the median is preferred, but you have the maximum value, the minimum, depending on your use case. You may prefer one or the other. And then you can also set up the scale in meters. This is a more advanced parameter, but basically this is the scale that the algorithm uses to sample the data from the original source when it is to summarize or to reduce the source to get the results in the specified geometries. So the larger this value is, the less operations will be done when it is aggregating the results. So depending on the size of your data and the size of your geometries, you may want to go for one scale, larger or smaller. Apart from the extension package that we have that contains these satellite embeddings, we are actually working on another extension package that allows you to actually analyze these embeddings and work with the embeddings very, very easily. This is not yet in production, but will be available very soon. And in the demo, I will show you actually how these components work, so that you start to get familiar with them. These basically cover all of the use cases that Caitlin was talking before, this change detection, similarity search, traditional machine learning. So this toolkit is very, very useful. In this new extension package that I'm talking about, it will include the components to run visualization, clustering, similarity search, and change detection. But we actually have already available another extension package that allows you to work with models. Basically, what this extension package, what it does is it grabs the capabilities of BigQuery ML so that you can train your models, run predictions, evaluate your models. And this is very good because it allows you to bring embeddings into predictive models directly using workflows, so you can have all your analysis together in the same tool. Apart from that, during the demo, I will explain more in detail how can we run visualization, clustering, similarity search, and change detection using workflows. But basically, the idea is that this set of tools allows you to understand what is your embedding representing, what type of information can we get from the embeddings, and it allows us to understand spatial patterns that are very easily that are very hard to understand if we just take a look at the raw data, because you will see that the embeddings are just like numbers that if we just directly take a look at them, it's very hard to understand. But if we use these tools to visualize them, everything makes more sense, and it gets easier to understand this way. So before going or jumping into the demo, I've prepared this slide here in which I explain the workflow that we will be following. I've prepared a few workflows and maps so that we can better understand how this works. But basically, the idea is that we are going to predict and map wildfire risk across different regions using these satellite embeddings. So the first thing that we are going to learn is how can we extract these satellite embeddings using workflows. Then we will run some or conduct some exploratory analysis on the embeddings just to uncover some spatial patterns and just like to get a first view of what is the information that these embeddings are giving me. Then we will use the embeddings to train a classification model that we will train it to predict wildfire risk in California. So we will use the embeddings as predictors, and then we will try to estimate whether there will be a fire or not in a specific region for a specific period of time. And once we have our wildfire risk index ready, what we are going to do is we are going to select those areas that are more prone to fire, that is, that have a high risk of wildfire presence, and we will use those locations to perform a similarity vector search analysis so that we can identify areas in Arizona that resemble these high-risk locations in California, so that we can get a proxy of what will be the risk also in Arizona. Imagine if we are missing historical data from Arizona, it's not very easy for us to run this type of models, prediction models. We can use the similarity search tool to try to get with insights, because this will also helps us enrich our analysis. So let me just go to the first workflow. Basically, what we are going to do here is just load the satellite embeddings. The first thing that I'm doing is just loading here a data set that contains all the geometries or the geographies for the boundaries for each of the states in the US. This is a data set that is available in our data catalog that we can just load here into the canvas and work with it. So the first thing that I'm going to do is filter and keep only the area of interest that we have, which is California. Now, I don't want to directly input this geometry into the Google Satellite Embeddings component, because this way I will only get one value for each of the features of the embedding for the whole California. But what I want is actually to have some granularity to be able to differentiate between the different regions. So I want to know what's going on in the different regions within California. So what I'm going to do is I'm going to make use of spatial indexes, in this case H3 cells, to split or gridify the area into smaller regions that then I'm going to be using to get the embeddings from. So this is what I'm basically doing here. As you can see now, the California has been gratified, and these are the input geometries that I will be fitting into the satellite embeddings component to get the values for the embeddings. So as you can see, what I'm doing here is just setting or saying the component what is the column that contains the geometry information. I'm explaining or I'm setting also that I want to get the embeddings from 2021 to 2024. And then if we go to the data tab here, you can see what's the actual output of this component. So we have for each H3 cell and each year that we've selected, all the values for all of the 64 embedding features that come from the satellite embeddings dataset. So now that we have the embeddings, as I was saying before, these numbers may be hard to understand or maybe hard to understand. So we have this set of tools that I've mentioned that we will make available anytime soon so that we can better understand what are these satellite embeddings telling us. So first, here I'm using the visualization component to visualize the embeddings. Basically, what this component does is it maps the embeddings by reducing the dimensions of the embedding. So as you saw before, these satellite embeddings have 64 dimensions, and visualizing all of them, it's very complex. So what I'm doing is reducing these dimensions into 3 so that I can visualize the embeddings as an RGB image. So this is basically what this component does. So you can do this automatically using dimensionality reduction algorithms like PCA. Or you can also set up, as you can see here, we have another option, which is manual, so that you can set up which features are each of the 3 channels that made up an image. We will see in a second how this looks like when we visualize the results in a map. But as you can see, the output of this component is just basically a color code that we can later use to visualize and see some patterns already in the embeddings data. And other things that we can do are clustering the data. This is also very useful again for visualization, but also to group the data based on similar characteristics so that we can uncover new patterns. This is very useful, for example, for segmentation or hotspot detection. And basically what it does under the hood is it runs a k-means algorithm using the embeddings as input features. So if I go to the next map, you can see how this looks like in practice. So on the left, I have the visualization of the image of the embeddings, and on the right hand side, I have the clustering output. As you can see, we can clearly identify different patterns. For example, this red region here is actually covered by it's a cropland. We have in blue and in green areas that are mainly covered by trees. So we can actually see how the satellite embeddings are capturing all these patterns, environmental climate patterns of the surface of the Earth. And with the clustering algorithm, we can see something very similar. And since we have information, temporal information, we can actually see how these clusters are changing through time. If we just filter this widget here, you can see that there are tiny changes from one year to another. So these are very, very good insights that we can get to start understanding what are the embeddings. Apart from these visualizations, we also have this change detection component that I was talking about before, which basically it allows us to detect temporal changes in specific locations. What this component does is it just computes the differences between the difference between the embeddings of a specific pixel or of a specific geometry for different time periods, so that we can get a map of how much each location has changed through time. And this is what we are going to see in the next map that I have prepared here. As you can see here, darker areas correspond to locations where the changes have been very small or no changes at all. And the lighter regions are areas where there has been greater changes, probably due to, I don't know, some reforestation or deforestation, wildfire presence as well, urban development, many things that, of course, we would need to run more deep analysis to understand. But as a first option, we can already see that there's changes going on, and this is a very good insight that we can get from the data. For example, if I just filter by a different date, we can see how the changes from one year to another differ through time. So now that we understand more, now that we better understand our embeddings, it's time to train the predictive model to estimate wildfire risk. So the first thing that we are going to do is to load into the workflow the wildfire perimeters in California. As you can see, we have them here, all of the perimeters of the different wildfires that have been going on since 2021. What we are going to do is just combine this information with the embeddings and include an additional label that we will use as the target variable when we are training our model. So basically, what we are doing here is to the embeddings we are adding an additional variable that just will be 1 when the area has been part of a fire and will be 0 otherwise. So we have basically a Boolean variable that says true or false depending on whether there has been a fire for a specific location at a specific year. We can see this here in the data. We have the H3 cell, the year, and the different features for the embeddings. And then we have this burnt variable, which is our Boolean variable that specifies whether or not there has been a fire for that specific location at that specific time period. Now that we have this ready, we can just split our data into training and testing. We will use the data up to 2023 to train the model, and then we will run predictions to 2024, because what we want to do is we want to create this wildfire risk index for the year of 2024. So basically what we are doing here is we are using this BigQueryML extension package that I was explaining before that has all of these components here that you can use to run classification, regression, forecasting, and things like that. So what we are going to do is just create this classification model that it's a very simple model. We have different options. In this case, we're using random forest and setting up different parameters. These are the same parameters that you have available if you are using directly BigQueryML to train your models. And then we can evaluate the performance of the models and run predictions. If, for example, if we take a look at the evaluation metrics of this model, we can see that these are the results. This model may not be perfect, but that's just for the purpose of the session. It's just fine. And we will see in a second the results of the predictions. We can use this predict component here just to run predictions for the year of 2024, as you can see here. And the actual output of this model is whether there's a fire or not. But we are not interested in this Boolean output. But what we want to get is the probability that this Boolean is true. That is, what is the probability that there's actually a fire in a specific location. So that's what we are doing here. We're just extracting this probability value from the output of the predictions. And then what we end up with is just a table in which we have for each H3 cell in 2024, what's the burnt probability? That is the probability that location there's a wildfire in a specific location. And we can see the results of this probability map in the next map that I have here, which is the map that I have on the right. As you can see, it gathers the information quite well, because we can see that the risk is higher in areas where there has been fires in the future. And also there's something that's very interesting, because this pattern that we can see here actually resembles the original visualization that we had from the embeddings. This means that the environmental patterns and the vegetation and the land cover are key to estimate wildfire presence, because there are some regions that are prone to fire presence and others are not so prone to fires. For example, as we mentioned before, these are mostly covered by trees, and we can see in this map here that actually the areas that are more covered by trees tend to have more fires than, for example, croplands here. This is all for the prediction. Now that we have the model, the index, the wildfire risk index ready, what we are going to do in the last workflow, very, very quick, is we are going to take those regions that have a largest wildfire index, and we are going to look for similar areas in Arizona. So this is what we're doing in this workflow here. I'm just right now filtering the wildfire risk index data and keeping only those locations that have a probability of fire larger than 0.7. And then I'm here extracting the embeddings of Arizona in the same way as we did for California. Then we can just use the similarity search component to run the similarity search, and we will end up with something like this. As you can see here, these are basically specifies, or the component gives us a similarity score that measures how similar the areas are with respect to the reference locations that we had in California. So here in dark, we have those areas that are more similar to those with fire, that are prone to fire, meaning that the risk will be higher in these regions, and in yellow we have those regions that are less prone to fire. We actually wanted to test that the similarity score that we got, it's actually meaningful, and we looked for an actual burn probability estimates for that 2024 year. We used, as you can see in the workflow, if we go back to it, we used data provided by the wildfire risk to communities model. That is a raster data that has the burnt probabilities of fire, and we just compute the Spearman's rank correlation coefficient of the actual values with the ones that we got from the similarity results, to make sure that we were not getting a value that was for which the correlation was very, very, very small. So in this case, we get a correlation of almost 0.6, I think, which is good. And if we also take a visual comparison, let me just show you the raster here. We can see that the patterns are pretty similar. Of course, there are some areas in which we are not getting the actual, we are not getting a risk that is as higher as the one in the ground truth. But this maybe, or this can be explained by the fact that wildfires may arise under different environmental conditions. So this condition, the environment here, or the Earth's surface here, may be different from the one that we used as reference in California, but that doesn't mean that this is also that doesn't mean that it's not possible that there's also a wildfire in those regions. So this is also something to take into consideration. So I know it has been a bit fast. So I think it's great that we have time now for the questions, in case you want to focus on specific things that we've covered that you have not understand, or that you want to know more about. Yeah. So
we did have a question in the chat. I think this one might be for you, Lucia.
okay.
For the similarity search component, can CARTO natively use BigQuery's vector indexes?
Yes. So actually, for the similarity search component, let me see if I have it here. We are using the vector search option that a store procedure that BigQuery has available, and it works with vector indexes, which actually what it does when you are using vector indexes, you are optimizing the search, because running these vector sets can be very, very costly, because vectors are very large, and you may have very huge data sets if you want to run similarities or compute similarities between many vectors. So BigQuery has this option that you can create vector indexes that actually optimize the search and runs like it runs like an algorithm that it's like an optimal algorithm instead of the brute force one. So instead of computing all the possible distances, it optimizes that search so that it's faster. And we have that option, but we've just included that in the advanced options, because it's not for all users. You need to actually be familiar with this component, with this store procedure in BigQuery, but you can do that as well if you're working with very large data sets and want to optimize the search so that it doesn't take as long to compute.
Okay, thank you. We did have quite a few questions that were answered by Caitlin, so thank you. But I'll read some of them in case you'd like to add a bit more from you, Lucia.
Okay.
We have one here. Does the satellite embedding component support other input types apart from geometries, like spatial indexes or rasters?
Now it does not. It only works for geometries. So if you, for example, are working with H3 or quadbeam, you cannot like directly input the indexes, because we actually need the geometries, because we need to intersect those geometries with the raw satellite embeddings, so that we can get the reduced versions. So for now, it just supports geometries. This is also a limitation that comes from the fact that we are using Google Earth Engine capabilities to do this. And for now, I don't think using other types as apart from geometries is also supported. But if in the future this is available, we will for sure include that here.
Great. We also have a question from Nestor. What is the degree of reliability of the detected patterns versus reality? I know, Caitlin, you replied in the chat, but if you'd like to say more.
Yeah, I mean, what I replied in the chat, right? So all of the base sensors here, the optical data, the radar data, anything that those sensors can see, that's what, will be represented in the embedding. So we're not really finding, and trust me, we have extensively checked for any like erroneous noise features that are generated, but we're really seeing good correspondence to the actual sensors themselves. And as part of, again, I didn't have time to really fully explain it, but it is covered in the paper. All of the individual pre-processing needed for the radar data, whether that's like spectral noise filtering and things like that, has been performed for each of these. So we've really made a serious effort to clean every individual data source as appropriate to make sure that the signals we are detecting are actually real. So, if you find a fake, pattern, a noisy pattern, please let us know. But I would say they're pretty accurate for the most part. And as you just saw in Lucia's demo, right? I mean, you could see the information pretty crystal clear. So, and I don't just have to say that. I would be on. We wouldn't have released it if there was fake patterns being in there. But no, it's pretty accurate. It's really impressive. So.
Great. And I think we have time for one more question. Let's see. I see a question from Alfie Long. Are there pen portraits or characterizations of the kinds of information and, I guess, data used within each of the 64 different bands?
Yeah, and this sort of touches on another question that someone else has. That I would say, excuse me, if there is one downside, if you can call it that, it's that this whole process is a bit black boxy, right? So the 64 dimensions, the embedding vectors are not as easily interpretable as some of the physical data you would receive from a sensor, right? So optical data is surface reflectance, and there's an easier way to sort of like conceptualize what that really means. But you can't necessarily infer any one, NDVI or a standard sort of thing from the embedding bands. Each one is, that that feature representation of all of that information synthesized. So it is a bit of a mystery flavor lollipop there.
Great, and that's time. Thank you everyone for joining, and thank you Caitlin and Lucia for such an insightful session. We'll be sending the recording of this webinar and the presentation to you all within the next few days, and that's all. Thank you for joining.